Okay, so good noon everyone and welcome to the Mastering Up International Conference Series 2025 to 2026. Today's theme is International Conference on Mechanical Engineering and Advanced Manufacturing. Super exciting stuff. Again, big cheers to Dr. Selvam Chandrasekharan and all our amazing participants. You all rock. So let's keep it chill, interactive and fun and grab your coffee and let's dive in. So ladies and gentlemen and dear friends, a very warm welcome to all of you. It's an absolute delight to have you here for today's exciting session on performance of heat sink with carbon-based nanofluids for electronic cooling applications. Now I know that sounds super technical, but trust me, we are going to explore some really cool concepts that connect science, innovation and the future of electronics. As technology advances, keeping devices efficient and cool has become one of the biggest challenges, and that's where carbon based nanofluids come into play. Today's session is all about how these futuristic solutions are transforming electronic cooling systems and paving the way for smarter, faster, and more reliable devices. So, whether you are a researcher or a student or just curious, this is going to be a fun and insightful ride. Let's kick things off with a motivational thought. Innovation is seeing what everybody has seen and thinking what nobody has thought. So let's keep our minds open and dive in with curiosity and explore how science and creativity come together to shape the future of technology. Before we begin Dr. Selvam Chandrasekharan session, I would like to take a moment to introduce him. So, alright everyone, I hope you are ready for some serious inspiration because today we have the absolute honor of welcoming a truly remarkable personality to our session. So, please join me in giving a warm welcome to Dr. Selvam Chandrasekharan, Associate Professor, Department of Mechanical Engineering at SRM Institute of Science and Technology, Katangulathur, Chennai, India. Dr. Selvam is a leading researcher in the field of nanofluid heat transfer with a doctorate from Anna University, Chennai. His expertise spans across heat transfer enhancement using nanofluids, refrigeration and air conditioning, thermal energy storage and thermal management of advanced systems like concentrated photovoltaics and thermoelectric coolers with numerous publications in reputed international journals and two granted passions and experience in editing special issues. His contributions to thermal sciences are nothing short of remarkable. So what makes him even more inspiring is his global recognition. He has been listed among the top 2% most cited scientists in the world with an impressive hashtag index of 21 and I-10 index of 24. Beyond his academic brilliance, he is also a life member of the Solar Energy Society of India and Institute of Researchers in India. Let's set the tone with a thought reflects his journey. Excellence is not an act but a habit, and it turned passion into impact. With that, let's welcome Dr. Selvam and get ready to learn from his inspiring expertise. And before we dive into today's session, I would like to take just a moment to introduce you to something that's close to our hearts. Thames Tech Solutions, a proud Swiss venture that's changing the way we see and use technology. At Thames, we stand by three simple but powerful values: innovation, excellence, and affordability. Whether it's cutting edge engineering or next gen scientific tools, we believe everyone should have access to transformative tech. As a visionary, Steve Jobs once said, innovation distinguishes between a leader and a follower. And at times, we choose to lead with a purpose. From digital marketing and web design to AI powered tools, server management, and mobile app development, our work spans across industries like aerospace, medical applications, energy, and more. We don't believe in one size fits all. We believe in tailored solutions that help businesses thrive in a world that's constantly evolving. As Albert Einstein wisely said, strive not to be a success, but rather to be of value. That's our mission, to add real value through strategy, technology, and a mindset focused on progress. But what makes us most proud is not just our business, it's our impact. With our initiative Mastering Up, we are focused on empowering the next generation by equipping students, especially from rural and underrepresented areas, with real world skills for real world success. Because, as Nelson Mandela also said, education is the most powerful weapon which you can use to change the world. So, today, as we begin this session, let's not just learn, let's imagine, build, and shape a brighter tomorrow together. So, the future starts now. So, at the end, I would like to introduce to the motto of Dr. Selvam Chandrasekharan: cooling smarter and powering stronger, innovating heat transfer for a sustainable future. So I would like to hand over the session to Dr. Selvam, and also thanks a lot for joining us today, and over to you, sir.
Okay. Can you hear me, ma'am?
Yeah, yes, sir.
Okay. Good morning to all. Good morning, ma'am. First of all, I thank organizer Mastering Up for inviting me to deliver the keynote talk. I'll be delivering the talk in the title of Performance of Heat Sink with Carbon-Based Nanofluids for Electron Cooling Application. And moreover, before that, I want to say one more thanks to Mastering Up. You have to organize continuously. You can organize like this, like these type of conferences, and it will be useful for the faculty, scholars, and the students, because we can able to connect with them through online and in the weekend especially. So it will be useful. Moreover, it will be very very useful those who are working specifically. So even industry people also can connect when we are conducting this type of conference at the in the weekend. So it will be useful to everyone. So you can continuously organize this type of conferences through organize sorry to online or to hybrid. It will be useful. I have conducted around 3 international conferences, two online and one physical conference I have conducted. Around more than 2,000 abstracts we have received, and around 500, more than 500 I think so. That they more than 500 papers have been published in referred journals. So I have wide experience in the field of conducting conference in both mode. So you can call me for these type of conferences and keynote talk. I will help you to significant in order to conduct the conference significant. Okay. So I will move on to the topic. So before going to discuss in depth about the performance of each thing, I want to say some introduction about the. I want to give some introduction on the electronic devices, as well as why we have selected the heat sink for the perform. Why we have given the title like a performance of heat sink. That I want to say. So in the electronic devices, we need to cool the electronic devices. So that is actually we need now. The demand is increasing to remove the heat from the electronic devices. That has been increased. So we need to go for a specific good method to remove the heat from the electronic devices. So what are the problems we are getting from the electronic devices, and how can we achieve that? How can we effectively remove the heat from the electronic devices or electronic chips or electronic circuits, so whatever it is. So it can be clearly you can able to understand from this presentation. So before that, before going to the topic, in-depth topic, I want to give some introduction about the problem in the electronic devices. Okay, actually we have we need efficient thermal management system device. Sorry,
Hello, sir.
Madam, am I
Yeah.
audible?
Yeah, yes, sir. Just you can continue.
Okay.
Yeah.
Yeah. Sorry for the disconnection. Actually, power
It's
cut actually here in
okay.
the
It's okay,
area.
sir. It's
So
okay.
that the Wi-Fi has been disconnected.
Okay, okay.
So now I have connected with the mobile. Okay.
Okay, great, sir.
Okay.
Yeah.
Okay. Fine. So actually, I will start from the beginning. So before going into the depth one, I will give an introduction to the electronic devices. So
Mm-hmm.
what are the problems we are getting in the electronic devices? So actually we need the efficient thermal management technique for maintaining the temperature in the electronic devices.
Sir, could
So
you
it
please
is
share your
crucial
screen
one
also?
for, yeah, I have shared already.
No, actually, it's not visible.
Oh, oh, sorry. Okay. Can you able to see now?
Just wait, sir. Actually, it's loading.
Oh.
Yeah, okay, sir. Just, yeah, now
It
visible.
is visible,
Yeah,
no?
yes.
Oh, okay, ma'am. Thank you. So, actually, efficient thermal management technique is needed for maintaining the temperature in the electronic devices. So, it is crucial one for the effective performance of electronic devices. So, requirements on miniaturization of electronics, we have carried out the literature and we have found out the requirements in order to maintain the temperature or in order to maintain the good performance in the miniaturization of electronics. So we need to, in the future or in the present, we may need the compact electronic system. So reduction in size is required initially, and higher processing speed also we may require. At the same time, after reducing the size, after getting the, when it is going for the higher processing speed, that time higher heat flux density will be happening. So it will come. So because of maintaining temperature at higher heat flux density is very critical, and it is crucial. So these are all we have identified, and this one is actually identified problem from the literature. So at the same time, when we are going for the reduction in size as well as higher processing speed, the heat flux will be increased up to 100 watt per centimeter square at peak operating condition in the electronic devices. So this will result in failure of electronic components with the increased heat flux density. So what we have to do, we have to go for effective cooling system or effective thermal management technique. So in that we have identified from the literature as well as based on the experience, we have already identified several methods, and we have implemented and studied. That I will be sharing today. So before going to discuss about what we have done with respect to the electronic cooling, before going to discuss about that, we should know the concept what we are doing with respect to the power. So actually, as I told, the demand to enhance the heat transfer rate from the electronic devices is increasing. So how can we achieve that? There are two ways to achieve the to increase the heat transfer rate from the electronic devices. Actually, we may know how to find out the heat transfer rate from any devices through the fluid or gases, sorry, liquid or gases. So through the Newton's law of cooling, we can able to find out the heat transfer rate from any devices, or when the conduction is present, we can able to find out the heat transfer rate with the use of Newton's law of cooling. Q equal to HADT. So Q is the heat transfer rate, and H is the heat transfer coefficient, convective heat transfer coefficient, and A is the surface area of the device, and delta is the temperature difference between surface temperature and fluid temperature. Okay. So there are two ways are there to increase the heat transfer rate. One is increasing the convective heat transfer coefficient, another one is increasing the surface area. So in order to increase the surface area, we can able to add the fins on the surface, and we can able to increase the surface area. With respect to the electronic devices, in the small space, we cannot able to add more fins. Already in the heat sink has been which has been used in the electronics, so that has more fins. Okay, in the small space, we cannot able to add the large number of fins. So many studies have been done with respect to addition of fins for increasing the surface area. But we may need, as I told already, we may need compact in size of the electronic system. At the same time, for the given space, we cannot able to add more things. So there are many restrictions in that. We should not increase the weight of the system also. So we may go for increasing the transfer quotient. So for increasing the heat transfer quotient, we may need some innovative heat transfer fluid like nanofluid or some other. Okay, so we have done with the nanofluid. So what are all the parameters we have considered? What are the points we have received from the literature? That I will explain now. Okay, and before going to discuss about that, we should know what are the thermal management methods are there for electronic devices. Okay, there are two methods we have: direct contact with the transfer fluid, another one is indirect contact with the transfer fluid. And in the direct contact, we have several types: air cooling, spray cooling, and immersion cooling, jet immersion, droplet electronic. Actually, in order to implement this electronic direct contact with the transfer fluid, many difficulties were observed, and uh, from the literature also they have stated that there are many things need to be changed in order to implement the direct contact heat transfer fluid. Okay, so many literature and many researchers have done the literature, have done the research works with respect to the indirect contact with the heat transfer fluid, and most of them use microchannel. In that many types we have, okay, microchannel cooling and heat pipe, thermoelectric cooling, rapid. PCM. In that two methods, most of the researchers have used. One is microchannel cooling, another one is PCM. We have also used PCM cooling for the solar cooling, solar panel cooling or the concentrated photovoltaics cooling. I have done one PhD scholar. I mean, one PhD scholar has been graduated under my guidance with the use of PCM cooling. And now with the PhD scholars and with the BTech students, MTech students, I am doing the work with the microchannel cooling for the electronic devices. Okay. So now in the recently most of the research papers also we have found microchannel cooling most of them used. So we have used the microchannel cooling with the liquid. Microchannel liquid cooling is available. Always we have microchannel air cooling also. Normal CPU should take a microchannel air cooling, or we can say heat sink air cooling. Air cooling with the heat sink. In the normal CPU, back side if you see one heat sink and one fan will be there. So that is actually heat sink with fan or heat sink with the air cooling. Okay, so like that we can able to say. So microchannel cooling, we have space for the liquid cooling, liquid flow. Okay, we have space for liquid flow that can be called as a microchannel cooling. Okay, so we have used microchannel heat sink for the for maintaining the temperature in the electronic devices. Okay, so in that I have also used the nanofluid. Okay, nanofluid, you may know, most of them may know the dispersion of solid nano-sized particle in space is called as a fluid. It has been introduced by Dr. Chai in Afghan National Laboratory year 1995. So why we are adding that? I mean, why we are adding the nanoparticle use? So in order to increase the thermal conductivity and heat transfer coefficient or conductivity transfer coefficient, that we have discussed. I mean that we have investigated in the work and that will be presented today. Okay. So now we have identified microchannel cooling is important. That can be applied easily, and we can able to go for the nanofluid. But which nanoparticle can be selected, which base fluid can be selected, that will come as another question. So if you see the material properties of nanoparticles or materials, okay, any material, metallic solid or non-metallic solid, if you see, you can able to observe the thermal conductivity at the same time. For preparing the nanofluid, we have to see how much density value it has. Okay, I mean nanoparticle density. Okay, so in order to maintain the stability of the nanofluid, the density is very very important. At the same time, to increase the thermal conductivity of the nanofluid, the thermal conductivity value also important. Okay, even if the thermal conductivity value is very very higher, but density is very very higher, that won't be significant because it will increase the thermal conductivity. At the same time, the stability of the nanofluid will be very reduced. So we have to focus on both thermal conductivity as well as density. So in the metallic solid, if you see, so you can see silver and copper having high thermal conductivity more than 400 watt per meter. Okay. At the same time, you see the density it has higher. Okay, and when silver has 10,525 kg per meter cube, and copper has 8,950. Okay, so these are high density. So because of high density, the stability of the nanofluid will be reduced. So if you see the non-metallic, you can see the graphene nanoplatelets and carbon nanotube. It has high thermal conductivity. Graphene nanoparticle as nanoplatelets as 3,000 meter cube, and carbon nanotube has 2,500 to 3,000 watt per meter Kelvin. It has been varied from 2,500 to 3,000. At the same time, if you see the density, it has compared to other networks. Okay, they are having low thermal conductivity as per the and GNP, I mean graphene nanoplatelet as 2.1 gram per cc, and CNT as 2500 kg per meter cube or 2.5 gram per cc. It can be varied from 2.5 to 3 gram per cc. Okay. So at the same time, we have to know which basically will be feasible for the electronic cooling and any other application if you go for nanofluid. We have yes. For example, I have done the work for the automotive cooling also. For that, I have selected water and ethylene mixture as a base, not to avoid the freezing in the winter season. Okay. So we have to see the application also. For the electronic cooling, there won't be no freeze. So you see water, so it has thermal conductivity up to around 0.62 watt per meter cube. Okay, so what is sufficient transfer fluid for any application except freezing applications. Okay, when you are going for freezing application, we cannot able to select because it will be freeze. It will start to freeze. So we are go for ethical or ethylene level water mixture for automotive and for another other freezing applications. Okay. So that is not spoke in the presentation. So with respect to the thermal conductivity of a surface fluid, waste heat transfer fluid. So we can be able to use the water as a heat transfer fluid or base fluid for the electronic cooling application. So now what we have selected and with respect to the thermal conductivity and density, in my work we have selected uh, graphene and CNT. At the same time, density and thermal conductivity value we have checked the values and based on the values only we have selected these two materials. Initially we have tried with the graphene nanoplatelets, and we have used the CNT along with the GNT like hybrid nanoparticle that has been used for our work, and we have produced the result that I will show today. And now we have selected the carbon-based nanoparticle that is actually hydrophobic in nature. So that one easily mixed with water. So we have extended that into hydrophilic. So for change it in order to change from hydrophobic to hydrophilic, we can able to go for two methods. One is surfactant method, another one is acetate. Okay. So surfactant can be used to reduce the surface tension of the base fluid. So surface tension will be reduced. At the same time, after adding the surfactant in base fluid, density will be increased, slightly it will be increased, and it will reduce the surface tension, and then it will increase the immersion of the particle. So it will increase the stability. Okay. At the same time, it will increase the density, it will create some other problem. So in order to avoid this, we can able to we will be able to go for surface modification also. Okay. So surface modification of nanoparticle by concentration that can be done. So in that it won't change any surface tension, but the particle hydrophobic in nature that can be changed into hydrophilic. Okay, so directly hydrophilic nature nanoparticle we can able to disperse in the water. Okay, that we have done. Actually, we have done with a surfactant also, but I didn't show. I have not going to display that. Okay, so I will be going to present with the surface modification of nanoparticle. Okay, so functionalization we have done with with concentrated nitric acid. So one waste nanoparticles we have taken. I mean these nanoparticles have been taken separately. Initially in reflux sensor at 400 rpm at 100 degrees Celsius for 2 hours, we have treated with the concentrated acid, nitric acid, and finally after 2 hours it has been done with water and filtered till reaching pH value of 0. Okay. After that, the particles have been dried in 150 degrees Celsius 6 hours. We can produce the dried and functionalized graphene plates or functionalized multi-wall carbon. Okay. So after concentration of nanoparticle, we can able to go for the nanofluid preparation. There are two methods are the one is one step method or another one is two step method. In one step method combines the production of nanoparticle as well as dispersion of nanoparticle. Many chemical and physical techniques might be involved in that. So that is not there in our scope, mechanical engineering scope. Okay, so this people are chemistry, chemical people will do that. Okay, and then many disadvantages there in the system. So since they are mechanical engineer, we will be using the quantity of nanofuel will be very higher, like 1 liter, 2 liter. So that cannot be produced effectively with the in a DNS water. Okay. So initially we have conducted the experiment, we have prepared nanofluid 0.01 percentage.
Actually,
Okay.
sorry for the interruption, sir. Could you please share your screen?
Yes.
Okay.
Oh, what happened?
Actually, you
Oh,
left the
sorry.
meeting. Okay.
I don't know what happened.
Okay, okay, no problems.
So I think there is issue with the network connection.
Yeah,
I
okay,
have
okay.
connected with the mobile network, so still power didn't come. Okay. So can
Okay.
you able to see now? So when
Actually,
is it has been disconnected, ma'am?
okay, just a few minutes before
From
only,
this.
but now I can't able to see
Okay.
the presentation.
Oh, is it okay, ma'am?
Actually, it's loading. Just wait.
Okay.
Yeah, no, okay, sir.
Okay, fine. So nanoparticle functionalist nanoparticle we have done like this. We have prepared the nanofluid like this. Okay. So base fluid, I mean functionalist nanoparticle has been mixed with the base fluid with the use of probe sonicator. So ultrasonication has been done with the help of probe sonicator and nanofluid has been produced. Okay. If the functionalist nanoparticles have not been used, you can add the surfactant along with the base fluid. So that can be done. So we can able to prepare the nanofluid with the use of surfactant also, but it will be increased. The density will be increased. That is why we have gone for the first stage nanoparticle. At the same time, the stability will be more. I mean, the stability of the nanoparticle will be maintained up to 1 month or 1.5 month or 2 months like that. But if you are going for surfactant, it will increase the density as well as the stability duration might be reduced. Since we have observed more than 1 month, we have a stability with the use of functionalized nanoparticle. But when we are going for the surfactant, it might be reduced, like a 15 days, 20 days like that. But it will be stable for a particular duration. And initially, we have selected the deionized water and the graphene nanoplatelets as a nanomaterial. Okay, and initially we have selected the volume concentration up to 0.01 volume percentage. And we have conducted the experiment and we have found that the conductive transfer coefficient improvement in conductive transfer coefficient is very less. So after that, we have fixed the several volume concentration by with the steps of 0.05%. So from 0.05 to zero point 0.2 with the steps of 0.05 we have varied, and these concentration have been fixed. Beyond zero point 0.2 the pumping power will increase and pressure drop will increase. Because of the pressure drop, pumping power will be increased. Okay, so that is why as per the literature also we have restricted up to point. And we have used the hybrid nanofluid also. I told we initially we have selected graphene. After that, we have selected uh, we have dispersed both nanoparticle in the water, and we use the hybrid nanofluid in the ethylene also. So we have observed this improvement. As per the literature, we have selected the hybrid as well as we have tested as compared to the mono nanofluid, I mean single nanofluid, single particle containing the nanofluid containing single particle, that is called mono nanofluids. Okay. As compared to mono nanofluid, hybrid shows good performance. That is why we have gone with the hybrid, as well as why we have selected carbon nanotube and GLP. A few researchers have gone with a different nanoparticle like uh, copper and carbon nanotube, silver and carbon nanotube, silver and graphene. Like that, many of them gone, but that won't be feasible based on our observation. That won't be feasible. Okay, so it can be feasible based on their observation, but based on our observation, it won't be feasible. But technically speaking, so we have selected graphene nanoplatelets. You can able to see this is graphene nanoplatelets, and the agglomeration of graphene nanoplatelets will be avoided when we are going for graphene nanoplatelets. So it will be arranged like this or like this. So agglomeration or stacking of graphene sheets won't be occur in the particular hybrid nanofluid. Okay, so it will be feasible. At the same time, the agglomeration or stacking of GNP sheet will be avoided. So it will increase the transfer of energy through the nanomaterials in the base load or in the fluid. Okay, so at the same time it will increase the thermal conductivity. At the same time it will increase the conductivity transfer coefficient also. That is why we have gone with the nanoparticles. And we after preparation we have done the stability characterization with the use of zeta potential distribution. So as per the literature, it should be zeta potential value should have more negative than minus 30 millivolt or more positive than plus 30 millivolt. So we have taken the zeta potential after the preparation in day 1 itself, after day 10, after the preparation in day 10, day 20 or day.
Hello, sir.
Yes, ma'am. There is a disconnection in the mobile network.
Okay, okay, it's okay,
I
sir.
okay. Well, few seconds, ma'am. I join again.
Okay, could you please share your screen also?
Yes, yes, ma'am.
Okay.
So I'm getting it. Wait. Can you able to see, ma'am?
No, sir.
It might be loading now.
Okay.
Please wait
Okay, okay.
seconds. It is visible now. Is it visible?
No, sir. Okay, yeah, now okay.
Okay, fine. Okay, after preparing the nanofluid, we have done the zeta potential distribution, and we have observed that the fluids were stable to 30 days. Okay, in the day one, we have got minus 44.440 millivolt, and day 10 minus 8.2 millivolt, and day 20 minus 36.80 millivolt, and day 30 minus 33.44 millivolt. So it was stable up to 30 days. Based on our observation, it can go up to 35 or 40 days. Okay. So beyond that, still a little settlement we have observed. Okay, after 40 days or 40 days we have observed. So we can go up to 35 days, 30 days like that. Okay. Even we can go up to 44 or 40. And this is for zeta potential of hybrid nanofluids. Okay, so it was found as compared to a mono nanofluid like GNP alone, as compared to that hybrid nanofluid shows best stability as that. Okay, and these are the measurement of nano properties also we have carried out. So we have measured the thermal conductivity with the use of KD to pro thermal property analyzer. In that we have measured the thermal conductivity and the density we have used. We have measured using the weighing balance. Okay, so as you know, the density is mass per volume. So, but the use of that concept, we have found the density using the weighing balance. And discussed we have carried out the use of normal bowling jelly rheometer. Okay, in that we have carried out the viscosity and the specific capacity we have carried out with the use of differential scanning colorimetry. Okay, in that we have found the CP value. Okay, specific capacity, and these are all the experimental test facility. Okay, so we have purchased the micro channel heatsink and we have used for the cooling application. So along with the micro channel heatsink, we have actually we have not used the actual electronic system or electronic device. We have used the heater. Two heaters we have used. Okay, not to effectively maintain the temperature, we have used the two plate heaters. Okay, so that heater has kept the heatsink base, and then in constant temperature we have made.
Hello, sir.
Yes, ma'am, yes, ma'am.
Okay.
Actually, the mobile network is low range.
Okay, okay. It's
It
fine.
has low range, ma'am.
Okay.
That is the issue. There on, I'm continuing in the where I missed, right?
Okay, yeah.
Okay. I'll share, ma'am.
Okay.
Can you able to see?
Yeah, yeah, okay, sir.
Okay, fine. Thank you. So actually, we have used the heatsink. We have not used the actual electronic device or electronic circuit. We have mimicked the electronic device as a heater. Okay, we have used the two heater and the insulation Teflon sheet has been provided on the bottom, because whatever the heat generated by the heater, that should entire heat should go to the heat sink. That is why we have done the we have coated the insulation, we have included the Teflon sheet. Okay, so whatever the heat generated in the heater, that will pass to the heat sink. Okay, so here nanofluid will be forced by the pump through the flow meter and to the microchannel heat sink. The heat and nanofluid will come out and it will go to the radiator and it will be cooled by the radiator, and it will be again it will be reached the nanofluid tank. Again this process will be separated. It will be repeated. Okay. So we have fixed several thermocouples in order to observe the variation in temperature, fluid inlet, fluid outlet. If you see here, you can able to understand. We have fixed two sensors in the heat sink base. Okay, base of the heat sink, we have fixed the two thermocouples. Okay, and two thermocouples have been fixed in the nanofluid inlet and nanofluid outlet in order to observe the inlet and outlet temperature effectively. Okay. So after getting the base temperature as well as nanofluid inlet and outlet temperature, we can able to calculate the heat transfer rate. From that, we can able to find out the heat transfer coefficient. Okay. Also, we have this we have purchased. We have purchased and we have used microchannel heatsink, and this one we have done. Okay, we have done with the machining techniques. We have done this heatsink, and it has been used in the expert test facility. This has been done by BTech students. Okay, and these are the results of thermophysical property. If you see the thermal conductivity as per the standard, with respect to temperature, it is increasing. With respect to concentration, also it is increasing. As compared to the graphene nanofluid, the graphene multi-wall hybrid nanofluid shows the high thermal conductivity. It shows 24.6% enhancement in thermal conductivity at 60 degrees Celsius. And density as per the standard, with respect to temperature, it is decreasing, but with respect to concentration, it is increasing. Okay, so but the increment in density with respect to the graphene nanoplatelets, the increment in density is for 4.09% only. But when we are dispersing the graphene and multi-wall carbon nanotube in the base fluid, so the increment is observed to be 14.7%, because the multi-wall carbon nanotube has high density as compared to graphene. Like it has density from 2.5 to 3 gram per cc. So that is why the density increased significantly as compared to GN. And here viscosity also with respect to density only, similar to density only. So with respect to GNP nanoplate, I mean graphene nanoplatelets, we have observed 80.16% increment in viscosity, and while the increase in viscosity in the hybrid nanofluid is 115%. Okay, that we have observed, and specific capacity is reduced with respect to the nanoparticle. I mean, with respect to the volume concentration of the nanoparticles. Okay, with respect to GNP, it has been observed 2.3%, and the CP is reduced up to 31.86% for the hybrid nanofluids. And these are the results of convective transfer study. Okay, so initially we have studied the base temperature of the AC. The base temperature actually it can be we have considered that as electronic temperature. I mean electronic item temperature. Okay, so that is significantly reduced when we are flowing the pure water. That has been reduced even when we are flowing the water, pure water. You can see it has been reduced from for this. I mean, for this heat flux range, it has been reduced. It has been started around 43. Okay, from 43 to around 42, it has been reduced. So there is a reduction in temperature when we are flowing the pure water. But after inclusion of GNP, you can see with respect to the mass flow rate, with respect to the concentration, it is significantly reduced. So it has been reduced from 40 around 43 to 37. Okay, around 36.95 degrees Celsius. So this is only for 30 gram per second mass flow rate, and this is only for graphene. And at the same time, with the same heat flux condition, you can see the temperature variation when we are using the hybrid nanofluid. Okay, so that time the temperature is decreased up to 35.44. The increased percentage is 50 or 15.11%. Okay, so this shows the graphene, I mean hybrid nano fluids are showing the significant result as compared to mono nanofluids. And here also, here we have increased the heat flux. Okay, so with the increasing the heat flux, the temperature is increasing. I mean initial temperature is increasing, From that it is reducing. Okay, so from 56 to 47.37 degrees Celsius is reduced with the use of graphene nanofluids, and here with the use of hybrid nanofluids we are getting 43.81 degrees Celsius from 56.44. So reduction percentage is 17.66. So we have to reduce more temperature. The reduction temperature should be higher. So actually it is working with the hybrid nanofluid. Significantly it is working. And this is another graph, okay, with respect to the higher heat flux. So with respect to the higher heat flux, so graphene shows higher variation, okay. So here 70.24 it has been increased, decrease, sorry, hybrid nanofluid shows higher variation, okay. So you can see from 87.5 degrees Celsius the temperature is decreased up to 70.24. Here, from 87.53 to temperature is decreased up to 65.24 degrees Celsius with the use of hybrid nanofluid. So, it shows that the hybrid nanofluid is significant. Okay. At the same time, we can see the convective heat transfer coefficient. It is also increasing with respect to the mass flow rate. As you can see. At the same time, while increasing the nanoparticle concentration, it has been increased significantly. But if you see the percentage with respect to the graphene, 31.14 percentage, and with respect to the hybrid, 45.62 percentage we have got. And while increasing the heat flux, it has been increased with respect to the GNP concentration. It has been increased up to 44.475 percentage. While using the GNP multiple carbon hybrid nanotube nanoparticles, it has been increased up to 46.97 percent. Okay. So pressure drop as expected with respect to the volume concentration of the nanoparticle, the pressure drop is increasing, but at the same time the pressure drop is not increased more as compared to other nanoparticles, because as compared to metallic nanoparticle or metallic oxide nanoparticle we have less density of graphene as well as multiple carbon. Multiple carbon has a higher value as compared to GNP, but it is slightly higher. As compared to GNP, slightly it is higher. So it won't be big issue in the pressure drop. So as you can see, at the higher concentration of GNP, we have observed that 5.32 kilopascal pressure drop. But here 5.35, that's it. Okay, with the use of hybrid nanofluids. So there won't be big issue in the pressure drop. So similarly here also you can see. So while increasing the heat flux, it has been observed for the graphene alone 5.05 kilopascal, and pressure drop observed 5.15 kilopascal with the use of hybrid nanofluid. Okay. And these are all the summary and conclusion. So we have studied the performance of heat sink for electronic cooling application with the use of graphene nanoplatelets, day-ionized water as a mono nanofluid. After that, we have tried with the graphene multi-wall carbon nanotube, DI water nanofluid, and that is called hybrid nanofluid. That we have carried out, and we have observed the following conclusion. And with respect to the stability, both nanofluid shows the better stability, but as compared to mono nanofluid, hybrid nanofluid shows the higher value, higher zeta potential value. Okay, so it shows more stability. It has more stability as compared to mono nanofluid. And with respect to the thermal conductivity, we have observed 13.59 percentage with the GNP alone, and with the use of hybrid, we have observed 14.60 percent. And here density is increased. Actually, density should not increase more, but we have observed the higher density value with respect to hybrid nanofluid. Okay, in the hybrid nanofluid, we have got 14.70 percentage, while it is less in the mono nanofluid, 4.0. And with respect to viscosity, we have observed 115.46 percentage with the use of hybrid nanofluids, while it has been observed up to 80.16 percentage for the mono nanofluid, or for the GNP nanofluid. Okay. Now we have found the pumping power as well as we have found the heat transfer. For the use of hybrid nanofluid, we have got 30% increase in power, pumping power. At the same time, we are increasing the we are getting the heat transfer enhancement up to 57%. So there won't be big issue for increasing the heat transfer rate by increasing the pumping power. But pumping power also should not be increased more. That we should take care. Okay. So in our case, we don't have any issue for the with respect to the pumping power. We don't have any issue in the heat transfer. And the specific capacity we have it has been decreased up to 31.8 percentage for the hybrid nanofluid, and 2.3 only we have observed for the GMP nanofluid. And base temperature around 14 degrees Celsius we have observed base temperature decreased up to 14 degrees Celsius with the use of hybrid nanofluid, while it has been observed up to 8 degrees Celsius with the use of GMP nanofluid or mono nanofluid. And conductive transfer quotient, as I told, hybrid nanofluid shows 57.23 percentage, while it has been observed up to 46 percentage for the mono nanofluid. So, with respect to the results obtained in our work, so it has been indicated that the graphene, and as compared to the graphene nanofluid, hybrid shows better heat transfer enhancement. So, it could be possible or it could be prospect for the enhancement in the heat transfer for the electron cooling applications. So, these are all the publications we have published. Okay. So, few papers have been published in the NCR publications. It could impact factor. Sorry, I forgot to input the impact factor here. So most of the papers around 4 to 5 impact factor. Few papers around 2 impact factor. One paper we have published in the conference study. And I have also used the PCM cooling for several applications. So that I didn't show here, but that has not been used for the electron cooling application so far. But I am currently using that has been communicated to the journal. Maybe in the next keynote talk or in the next meeting, I can able to show that. And these are other reference that we have used for the previous thesis, and we have used for the published papers also. And so I'm looking for the full-time scholars, full-time research scholars in the field of thermal energy storage, heat transfer, electronic cooling, and thermal management of photovoltaics and electronic devices, nano energy. So interested candidate can contact me. Our university is providing around 31,000 for the non-gate, without gate or without net qualification. 31,000 they are providing now, and this will be applicable for 3 years. Okay, if you have a net or gate qualification, you can able to receive around 37,000. So you can contact me with this mail ID and WhatsApp number. So I am interested to take scholars. If masking up also could help me to find some scholar, you can share this slide to the participants so they can able to contact. Thank you. If you have any question, you can ask.
Yeah, sure. First of all, thank you so much for the wonderful session. So, in our first question,
Thank you.
how can carbon-based nanofluids improve the efficiency of heat sinks in next generation electronic devices?
Yeah. So that's all now.
Yeah, yes, sir. That's our
That
first question.
one question. One
Yeah,
question. That's all, right?
yeah.
So actually, that for that only I have presented now. So here you see the thermal conductivity is increasing as well as the heat transfer quotient. Thermal conductivity is increased. Carbon-based nanofluid, it can be used GNP as well as multi-well carbon nanotube based on your budget. It can be used separately or it can be used like a GNP. I mean hybrid nanofluid. Okay, so both nanoparticles are, GNP as well as carbon nanotube will be significant for the enhancing the thermal conductivity, stability, and convective heat transfer quotient. So it has high thermal conductivity. Definitely, it will give some enhancement in thermal conductivity as well as in convective heat transfer quotient. Based on my work, so here we have observed the significant reduction in the base temperature of the heat. So from that we can able to understand the efficiency as well as the conductive transfer quotient of the in the electronic base. It will be increased significant. Sorry, it will be decreased significantly. I mean, base temperature will decrease significantly, and conductivity transfer quotient will be increased significantly. So definitely we can able to go for carbon based nanofluids. So this is the answer. Actually, it has high thermal conductivity. It has good thermal properties, and the variation, the transfer of energy through the particle will be significant. So definitely it will increase the efficiency and conductivity transfer quotient. That's all. Any
Yeah,
other thing?
yeah, thank you, sir. What are the potential challenges in scaling nanofluid based cooling systems for industrial applications?
Yeah. So industrial application, actually I will recommend the nano fluids. It can be used for small scale applications. Okay. Yeah, mostly because of stability of the nanofluid, it can't be used for the large scale application. So based on my observation, I am telling. So it can be used for small scale application. It cannot be go for a large scale industrial application. In the industrial also, they can able to use the heat pipe, for example. For heat pipe application, we might have need some low quantity of nanofluid, less quantity of nanofluid. So that can be appreciable. But when we are going for the large scale application, I won't recommend the nanofluid to use the large scale application, because sedimentation issue will come, and then after based on my work, so after 35 days or 40 days we cannot able to go for uh, same we cannot able to go for good, we cannot able to expect the good stability. So after 40 days we cannot able to use it. So I won't recommend the nanofluid for large scale application. Even if it is small scale application in industry, it can be used for heat pipe application, for small scale electronic cooling application. And one more recommendation: when the nanofluid is in continuous flow, it can be used, because if the stability is less also, when we are flowing with the use of pump with the active cooling, so it will, I mean, the nanoparticle will move along with the fluid. Even it has less stability, it will move along with the fluid, base fluid. So it will take some amount of heat from the surface. So heat transfer will be effective when the nanofluid continuously flows. But if it is not there, the large scale application in industries. That's it.
Okay, great, sir. Sir, what role could nanofluid cooling play in the future of high performance computing and AI hardware?
I couldn't get, ma'am. Can you repeat
Okay.
once again?
Yeah, what
What
role?
role?
Yeah, what role could nanofluid cooling play in the future of high performance computing and AI hardware?
And AI?
Hardware.
Yeah, okay. So previously I have explained. So it can be used. So I mean the role of nanofluid is significant. So initially we have to test with the base fluid. Okay, which base fluid is applicable for the particular application, and selection of nanoparticle is very very important. And which application you stated, ma'am, for this question? Which application?
Actually, it's not have any applications. Just asking
Hmm.
nanofluid cooling play.
Nanofluid cooling.
Play in the future of high performance computing.
Yeah, that is application high performance computing. Okay, as for high performance computing, when it is in flow, continuous flow, no, there is no issue. Okay, we can able to go for carbon based nanoparticles. With respect to the cost, you have to decide which nanoparticle can be selected. But carbon based nanoparticles are good. When it is in continuous flow in the high performance computing, also it can be used. Okay.
Okay, so thank you for the useful answers. They have been really helpful in clarifying the topic. I hope the participants were able to follow along and understand the key points shared. Your insights have certainly value added to the session. So, Dr. Selvam Chandrasekharan, on behalf of organizing team and all the participants, I would like to extend our heartfelt gratitude for joining us today and delivering such an insightful session on performance of heat sink with carbon based nanofluids for electronic cooling applications. Your ability to simplify the complex research and connect with it real world applications made this session both engaging and inspiring. Your work in the field of nanofluid heat transfer, thermal energy systems, and sustainable cooling technologies is truly remarkable. The way you highlighted the future possibilities in electronic cooling has sparked new thoughts and ideas among our participants. And being recognized among the top 2% most cited scientists in the world speaks volumes of your dedication and contributions to science, and it was a privilege to learn from you today. So once again, thank you, Dr. Selvam, for sharing your valuable time, knowledge, and expertise with us. We hope to have the honor of engaging with you again in future sessions and collaborations. So wish you continued success in your research and innovation that will no doubt shape the future of sustainable technology. So thank you, sir. Thank you so much.
Okay, ma'am. Thank you. I hope you will share the video, recorded
Yeah,
video,
sure, sure.
and certificate also, right?
Yeah, great.
And you can share my PPT. I will send you the PPT
Yeah, okay.
in a PDF format. You can share it to the participants.
Yeah, great. Super, sir. Great.
And you can also suggest some scholars if they want to do PhD under my guidance.
Yeah.
You can give the suggestion and you can share my profile.
Yeah, great. Sure, sure, sure. Yeah, thank you, sir. Take care. Bye bye.
Thank you so much.
Yeah.
Thank you. Bye.